Welcome back to Classical Mechanics 1. This is 15th of September, Thursday, 2022, and our 14th meeting. Yeah, so last time we were talking more about Newton's second law and Galileo's principle of relativity, as well as Newton's third law, superposition principle, etc. So we will continue with these concepts concerning forces. Yeah, any questions? Yeah, so last time I had said that I would just make a few remarks about the terms dynamics, kinematics, and statics, and what they mean. So to begin with, dynamics, it refers to the evolution of a system in time. That is the essential idea. Dynamics doesn't mean something is moving, but it is how the system behaves in time. So by this we mean the behavior of the system with the passage of time due to the forces in operation. So that is important. What forces are present, they are going to determine the dynamics. To understand the dynamics, we need to know the forces and interactions present. Interaction is another name for force, you could say, some sort of more general term. An aim of dynamics is to find the trajectory by solving the equations of motion. Yeah, so by now we have stated Newton's second law. So our aim is to find the trajectory by solving the equations of motion given initial conditions. So initial conditions are quite important in this process. So by Newton's second law, doing this requires the knowledge of forces. Yeah, so you need both forces as well as initial conditions. The result of this exercise for some initial conditions could be that the parts of the system do not move. Okay, so the system as a whole may not be moving, even the parts may not be moving. That may be the result of solving the equations or observing it. That is still called dynamics because you have accounted for the forces and solved the equations of motion. While for other initial conditions, the parts of the system may move. Okay, so that is also possible. Now, as a matter of language, the equations of motion of a system are also called the dynamical equations because they determine the dynamics. So this is our language. Any question about these terms? Okay. Now, let me say a few words about statics. So, I mean, it doesn't mean that statics and dynamics are opposites. Yeah, that is not the idea. So these are some terms that have become commonplace. So I just want to say what they mean. Statics refers to situations where a system does not change with time. Yeah, so that is a somewhat different idea. For example, a static solution of the equations of motion for a particle is one where the position is independent of time. So we will call it a static solution if the position doesn't change with time. To discover a static solution or several static solutions, we need to know the forces and solve the equations of motion. So static solutions are just a very special class of solutions, maybe ones that are a bit simple or the ones we first look at. sometimes. But to find them, you still need to know the forces. You need to solve the equations of motion to find static solutions. Okay. So on the other hand, there is another concept called kinematics.
No, in statics, R of t will be constant with respect to, you were saying that constant function.
Yeah, R of t is independent of time. So it's a constant function of time. Of course, you have in background some kind of frame that you're in, and it's all is referred with respect to that frame. And in that frame, and with respect to some fixed origin in that frame, we are saying that R doesn't change with time. If there is such a solution, we will call it static. It's also called a time-independent solution. Yeah, sometimes it's also called a stationary solution. Yeah, these words kind of get additional meaning and character in quantum mechanics, so one needs to use them a bit carefully. But for now, stationary, static, time independent all mean the same. Okay, any other question? All right. Now I want to say a word about kinematics. Okay. Kinematics is somewhat, I mean, I would not like to use the word opposite, but it is somewhat complementary to dynamics. The dynamics and kinematics are sort of complementary parts of the problem. See, very roughly speaking, yeah, but it's useful to have such a distinction sometimes. So kinematics refers to those aspects of a system and its motion that do not depend on the specific forces that act. Okay, so this is loosely the part of the problem of motion which doesn't concern itself with the forces in operation, but is concerned with other features. Now, what those other features may be? They may be things like the number of degrees of freedom of the system. Okay, that too is an attribute of the system. It helps to know that. The range of values that physical variables can take. So those are again kinematical aspects. How the values that physical quantities take change from one frame of reference to another. Okay, that again is not a matter concerning forces or interactions, but just how you want to view the system, from where or when, or yeah. Okay, let me remove the word when. When does involve dynamics, but from where or with respect to a moving frame, that kind of question. Now, as we mentioned earlier, the problem of finding the trajectory x of t or r of t from a known acceleration is simply a matter of integration 2 times. That part of the problem is called kinematical, okay, because by some luck, somebody gave you the acceleration and you only need to do some integration. And I'm not saying integration is a simple business. It can be quite complicated, but nevertheless, it does not involve physical knowledge of forces. Okay, so we want to make that distinction. On the other hand, finding the trajectory from the forces involves dynamics. Okay, so this is the main distinction. Okay, any question about this? Yeah. Okay, so otherwise, let me go on to one more important concept which you may have met before, and this is concerns dimensional analysis.
So we go up one.
Yes, yeah. So we started with this topic. Yeah.
Can you go down a little bit?
Go down a little bit. Okay, sure. Here you are. Or I can shrink this a bit.
Yeah. Okay, thank you.
Yeah. I forget who else asked me to move the things. I mean, is this adequate? Do you have any questions? Okay. If not, I mean, this is simply language, but we do communicate using language, and that makes it very important. Okay, and we also think using language. So it is important. Okay, so now I want to introduce the idea of dimensions, sometimes called dimensional analysis, and units. So very briefly, so physical quantities like the Cartesian components, the position of a particle, okay, so x, y, and z, or the time interval between two events, or a force, yeah, all of these physical quantities or variables can each be assigned a dimension. So it turns out that the dimensions of all the mechanical quantities we encounter, yeah, and we have encountered a few, we're going to encounter more as we go along, can be expressed in terms of three basic dimensions. These are the dimensions of mass, length, and time. Okay. So more precisely, any quantity f, by f I don't mean a force, but it could be a position or time interval or a torque, etc. It could be a vector, but then we will typically look at the components of a vector. Yeah. Can be assigned a dimension which is denoted with a square bracket. Yeah, so square bracket x would be the dimensions of x. And it is written as the basic dimensions raised to appropriate powers. So the dimensions of f may be m to the power of alpha, L to the power of beta, and t to the power of gamma. Okay, for some real numbers, alpha, beta, gamma. And then we would say that the quantity f has dimensions m to the alpha, L to the beta, t to the gamma. Okay. Now these numbers are typically integers. I mean, positive, negative, could be zero also. Yeah. Sometimes they are rational numbers. Now, if all these powers alpha, beta, gamma are zero, then we designate the quantity as dimensionless. Okay. So if that is the case, we say that this is a dimensionless quantity. Right? Now, consistency of equations requires that all the terms in an equation have the same dimensions. Okay? So it does not make sense physically to add a length to something with dimensions of time, or add a mass to a something with dimensions of length. Yeah. Or to add a force and an energy. So all terms in an equation must have the same dimensions. This gives a quick way of eliminating some errors in equations. Yeah. So simply check if all the terms in your equation have the same dimension. And as one deals with more and more sophisticated systems, one can make some mistakes, and this is very helpful. Yeah. I mean, vectors can also have dimensions. Yeah, so this is not restricted only to scalar quantities. A component of a vector can have a dimension. A vector as a whole can have a dimension. So force is a vector, it has a dimension. Okay, so let us look at some examples of dimensions of physical quantities. Of course, the basic ones I already said. So the mass of a particle has dimensions m, the length of a ruler has dimensions L, and time interval has time t. Then we can go to velocity. Velocity was x dot. So that is a length per unit time. So we have to build it up from there. Acceleration was x double dot. So you're going to get one more time to an inverse power, LT minus 2, LT to the minus 2. Momentum is mass times velocity. So mLT to the power of -1. So like this, we can continue force. And now we are going to turn things around. If you are given a physical quantity and asked its dimension, can of course go back to its definition if that is at hand, or you could use some equation that you know that it satisfies, and from that equation you can reduce its dimension. Okay, so for example, you know that Newton's second law says that force is mass times acceleration. So from that you can deduce that the force must have dimension mass times that of acceleration. Okay. Then you have, of course, energy. I haven't spoken about energy, so we will come to that shortly. Okay. Now, okay, question for you. What is the dimension of an angle? Please tell me.
Dimensionless.
Yeah, dimensionless.
Very good. So that was Krishanu, as well as I didn't hear who was the other. Suchit Kaustav. Okay, thank you. Yeah, that's very good. So angles have no dimension. So for example, yeah, I mean, there are many ways to look at it. How would you like to explain it? Please offer your suggestion.
It's a ratio of two lengths.
Indeed, very good. From trigonometry, we define angles. Yeah. Well, okay. Yeah. Indeed. Yeah. It's a ratio of two lengths, like an arc length and a radius. This kind of thing. So indeed, angles are dimensionless. Yeah. Or yeah. And for consistency, we talk about the cosine of an angle, right? So. And I spoke about the power series for cosine. So the cosine has a power series 1 minus theta squared upon 2 plus ... So if such a formula has to make sense, the dimensions of 1 and the dimensions of theta squared must be the same. And therefore theta must be dimensionless. Otherwise you cannot add it to 1. Of course, numbers like 1 and 2 are dimensionless. Okay, so quantities like pi and yeah, those are all dimensionless. Okay. All right. So we will look at more examples as we go along. Okay, so that is as far as dimensions are concerned. We have a related concept, namely that of units. Yeah, so let me. So when I say something has a mass of 1 kilogram, we are saying two things. First of all, that its dimensions of that of mass, and that its mass in some standard unit is 2. Okay, so what is that standard unit? So the most commonly used systems of units in mechanics are the international system and the centimeter gram second CGS systems. Okay, so of course conventions differ, and therefore we have different systems of units. Once in a while, people come together and agree that they will use some convention. So the SI is one of those agreements. Yeah. Okay, but depending on context, sometimes you prefer one system of units over another. It really depends on context. What would work in an engineering problem may not work in a problem of atomic physics. Yeah, so I mean, engineering of bridges has certain scales, and you want to work with things you don't want to work with very large or very small numbers. That is our human tendency. So we pick units that are suited to the set of problems that we want to look at. Okay, in the international system, abbreviated SI, System International, the basic units of length, mass, and time are the meter, kilogram, and the second. So that is presumably familiar to you, and the unit of force is called the Newton, and that is 1 kilogram meter per second squared. Yeah, so kilogram meter per second squared, MLT to the power of -2. Of course, the unit of force will change in other systems. So in the CGS system, centimeter gram second, the corresponding base units are the centimeter gram at second, of course, and the unit of force is called the dyne. So 1 dyne is 1 gram centimeter per second squared. Okay, and one can convert a gram to 10 to the -3 kilograms. A centimeter is 10 to the -2 meters, and second is of course a second. So this is 10 to the power of -5 newtons. Okay, so this is the conversion between dynes and newtons. You just have to convert the basic units. Okay, any question about this? So I would like to recommend that now onwards, when you write equations, please check the dimensions. Check that left-hand side and right-hand side have the same dimension. You don't have to check it every time, but once in a while, especially when you're in doubt, please do check it, and you will eliminate lots of errors. Okay. Any further question about this? So if you want to add a quantity and it's square, then that quantity must be dimensionless. Otherwise, it doesn't make sense. This is one basic concept that's worth having in mind. Okay. So now I want to give a few examples of forces and some of their features. First, gravity. So the gravitational force played a central role in the development of mechanics in the hands of Galileo, Newton, and their contemporaries. And their contemporaries were people like, okay, do you want to suggest some of their contemporaries? Any names occur to you? One is named after, a comet is named after that person. Who was a contemporary of Newton?
Halley.
Yeah, indeed. Halley's comet was a friend of Newton. And then there's another person whose name is assigned to the nature of force in a spring. He was another
Robert Hooke.
Yeah, Robert Hooke, indeed. Yeah. So, and there were definitely many others. I mean, these were three people who were all in England, but there were people in other continents as well. Yeah. So Newton proposed, or in the continent, the continent refers to Europe. So Newton proposed his universal law of gravitation and developed his laws of mechanics in large part to understand the motion of planets and comets. Yeah. And the moon, of course. Yeah. So yeah, and I will describe this a little bit later in a little bit more detail. I mean, especially Kepler's role in this matter, Kepler and Newton. But here I want to very briefly mention Newton's law of gravity. So Newton's law of gravity says that the force between 2 point masses, m1 and m2, and these numbers m1 and m2, these masses, strictly speaking, are called gravitational masses. Okay, so I will qualify what I mean by that. Yeah, but so just hold on. So suppose you have two bodies of masses m1 and m2. Strictly speaking, they have to be point masses. One can extend it to larger masses as well, but let's begin with this. So Newton's law of gravity says that the force is attractive and proportional to the product of these gravitational masses and inversely proportional to the square of the distance of separation. Okay, so that is a mouthful, but we can write it down as an equation. So we said that the force is proportional. Okay, so there is some proportionality constant involved. So the constant of proportionality is called Newton's gravitational constant in honor of Newton, denoted capital G. Yeah. So let's write down a formula. If R1 and R2 are the position vectors of the two particles, okay, at some instant of time. So you have two masses, m1 and m2. You have an origin here. You have the position vectors R1 and R2 indicated in this diagram. Then the force exerted, we have to be specific here, the force exerted by m1 on m2. M1 on M2. M1 is drawing M2 towards itself. Yeah, so the force would act in this direction. The force of M1 on M2. So it points from M2 towards M1 and is given by this formula. F1 on 2 is of course proportional to G, M1, M2 product of the gravitational masses divided by the square of the distance. Yeah. Okay, I've written it as a cube of the distance of separation and then put in the numerator a vector. Yeah, so that vector has to tell us the direction. So I've made it R2 minus R1 over here. So R2 minus R1, which way does that point? R2 minus R1 points towards R2. Okay, so R2 minus R1 is this vector, and you take away that vector, the R1 vector, and using the parallelogram law, you will find that R2 minus R1 points this way. So this is R2, this is minus R1. So can extend minus R1 here. And then you will get the parallelogram. From the parallelogram law, you find that this is the difference. So you parallel translate it there and find that is the thing. So R2 minus R1 points from R1 towards R2, and then you put a minus sign up front. Then it will reverse and point towards M1. Okay. Okay. So please look at this formula carefully and convince yourself that it points towards R1. M2 to M1. Okay, so this equation conveys, encapsulates everything we said before. Now, Newton's third law, by Newton's third law, M2 exerts an equal and opposite force on M1, given by F2 on 1 is equal to minus F1 on 2. Okay, so that is something we spoke about before. And by the way, these forces do not depend on state of motion of the particles. So it is at any one instant. M1 may be moving, M2 may be moving at the next instant, maybe somewhere else. It may be accelerating, it may be stationary, all that doesn't matter. This is the force at one instant of time. Yeah. Okay, any question? Okay. Of course, that is because the force is of a certain character. It doesn't depend on the nature of motion. It just depends on the distance between the objects. Okay, there are other forces that depend on the velocity of the body. So we can talk about that later. It'll come up in other contexts, like the force of friction. Yeah. Okay, so that is our first example of force. Now, I told you last time this superposition principle of forces. It is very useful. Let me briefly indicate one use of it. So Newton's law of gravitation, as I mentioned above, applies to point particles. Okay. However, it may be used to calculate the force due to extended bodies on point masses. You may have an extended body like a sphere, and you want to know what force it exerts on a point mass. Or you may want to know the force due to a point mass on an extended body. Or you might want to know the force between two extended bodies. Yeah, all these possibilities are there. In order to do this, one repeatedly uses the principle of linear superposition of forces. Okay, so that is the idea, which states that the force due to two objects on a given particle is the vector sum of the individual forces. Okay, so this is something we said last time. Yeah, so that is one very useful tool. A somewhat complementary statement is that the force on a composite body is the vector sum of forces on all its constituents. Okay, so let me give one example or a couple of examples. Yeah, so one nice result is that by using the principle of superposition, one may show that the force on a point mass that lies outside a spherically symmetric mass distribution. Okay, so this is something we frequently encounter. Suppose you have a spherically symmetric mass distribution. Yeah, so it has some center. So when I say spherically symmetric mass distribution, please, can you say what I mean by that? How would you make that precise?
mass will be a function of r only radius.
Okay. Yes, Aditya. So you are on the right track. So when you say mass, okay, I mean, mass is the mass of an object. So let's be a little bit more careful here. Would you like to use a different term? Yeah, okay, you're quite right. So the mass distribution depends only on the radial distance, indeed. So, or let me say, let's talk about the density. Yeah, it's a helpful concept to talk about a density, a local density, rho of some location. So it will tell you, okay, you tell me, what is the dimension of density? Mass density.
kg per meter cube.
Indeed, yeah. So mass per unit volume. Okay, so very good. Yeah. So several people have answered, in fact. Thank you. So anyway, the statement then, by density, we mean the mass per unit volume. Of course, in a limiting sense, infinitesimally small volumes, how much mass do they contain? This may depend on location, of course, but if this is a function only of the radial distance and not the polar and azimuthal angles with respect to this origin and some axes, then we will say that the mass distribution is spherically symmetric. Okay, so that's what we mean precisely. So suppose you have a spherically symmetric mass distribution and a point mass somewhere outside it. Then it is possible to show that the force that this external mass feels due to that spherically symmetric mass distribution is the same as the force due to a point mass with mass equal to the total mass capital M of that distribution, located at the center of the distribution. Okay, so this is a very useful result. I'm not deriving it for you here right now, but I want to mention it at the very least. That what would you need to do? You would need to account for each little mass in this distribution. You know what kind of force it exerts. Yeah. And you would have to add up all those forces. Yeah. So it is that problem. And
all the components will cancel off, right?
You're very right. You're very right. So the orthogonal components. So if there is a mass element over here and a mass element there, and they are equally at equal angles relative to this axis, then the components of the force in these orthogonal directions will cancel out, and you will be left with only a force that points vertically upwards in this picture. And using such an argument, you can show that the only force that survives, I mean, the vector sum points towards the center of that distribution. And you have to add up all those forces. It's possible to do that, or use a little bit of geometry and arrive at this conclusion. Of course, it needn't be a continuous distribution of masses. You could have several point masses, and you can ask what is their total effective force due to them. Let me give another example. Another nice example. For example, the force due to a thin spherical shell of radius r and mass capital M centered at the origin. Okay, so we've got a thin spherical shell. Let me draw the shell. Yeah, so the mass is concentrated on this shell. There's nothing inside, no mass inside. And now there is, of course, an origin at its center. Now, if you have a mass outside M, you can ask what force does it feel due to this spherically symmetric distribution on the shell. Well, it turns out it is given by, again, the same Newton gravitational law, G capital M M r hat upon r squared. Okay, so And this force points, of course, towards the shell, and r hat is the radially outward pointing unit vector at any point. Okay, so this is an example of a spherically symmetric mass distribution. Okay, so it is a special case of the previous discussion. Now we can ask a second question. Suppose your mass that you want, little mass small m, is actually inside the sphere. Okay, so not outside but inside the sphere. Yeah, so then what force does it feel due to the distribution of mass on the surface? Okay. So it turns out that the force vanishes inside the shell. So let us argue why this is the case. Yeah. Yeah, so Kaustubh has it right. The force is 0 inside. And there is a nice little geometric argument why this is the case. Let us indicate this. It is due to cancellation of forces due to diametrically opposite parts of the spherical shell. Okay, so that is the idea. So let's look at that. I want to know the force on this little mass here. So let us consider, let us break up this spherical surface into little portions, which are the portions that are internal to a cone that intersects the sphere, a cone with apex at the mass of interest. So we are going to then cover the entire surface of the sphere by many such little elements. Now, I claim that the force due to this patch, of course, it points in the leftward direction, and the force due to this patch points the rightward direction. Yeah, both are attractive. So supposed to draw those arrows carefully. Yeah, so yeah, so we have these two arrows. I claim those arrows are equally or of equal length and oppositely directed. Why is that? These diametrically opposite surface elements, so these things are called surface elements, have mass. How much mass is there in a surface element? Well, there is as much mass as proportional to the area. Okay, because we're supposing that it is spherically symmetric, so the density is uniform on the surface. So more the area, more the mass present. And since the area of the surface grows with the square of the distance from the apex of the cone, okay, so the area subtended by this cone grows with the square of the distance. Yeah. So there's more mass here than there is over there. However, this element is farther away than this element. And in fact, the distance, the force falls off as the inverse square of the distance. So the quadratic growth in the mass of an element is cancelled by the inverse square fall off in Newton's gravitational force. So we are supposed to account for both. So you can say delta F is equal to minus G small m some delta m upon r squared r hat, okay, where r is the distance from the apex of the cone to the element of interest. And the point is that delta m is itself proportional to r squared. So the r squares cancel out. So this is the delta f due to this element, and there's a similar delta f due to that element, and the two are equal and oppositely directed. Okay, so I've sketched the argument. One can try to make it a little bit more precise. Okay, so due to these cancellations from diametrically opposite elements, the total force on my mass m is 0. Okay, yeah. Okay, so this can be of quite a practical use. In fact, less so in gravity, more so in electricity, electromagnetism. So I will make a comment about that. Okay, but any question about the rough argument I just gave? Okay, by the way, as a matter of language, sometimes we call this mass a test mass. Yeah, so so that is just a language. Sometimes we are asking, we are probing what the force is at various locations. So we put a test mass there and either do a calculation or let it move and observe it, find the acceleration, and then deduce. So so that's the reason we call it a test mass sometimes. Now I come to a somewhat more subtle concept. This is an opportunity to say a bit more on the concept of mass. Okay, so let me say a little bit more. The mass mi that appears in Newton's second law, recall Newton's second law, inertial frame, mi times acceleration. This mass that appears here of a body is called the inertial mass. Okay. Okay, so that is the name given to it. Newton's second law is also called the law of inertia. Or rather, I think Newton's first law is called the law of inertia. I'm sorry. Yeah. So anyway, this mi is called the inertial mass. Now we have described using Newton's second law a way of assigning inertial masses to bodies relative to that of a reference body. Okay, so remember the method we adopted last time.
So that A2 by A1 that thing.
Exactly. You apply the same force, find the accelerations, take the quotient of accelerations, and thereby find the quotient of inertial masses. So then you know the mass of any body as a multiple of the mass of a reference body. Okay, so that was the idea. So suppose you have done that and assigned inertial masses to all the bodies of interest. Okay. That is as far as inertial mass is concerned. Now we have another concept. Okay, because just now we have stated Newton's law of gravity. It says that the force of mass 2 on mass 1 is g times product of masses divided by square of distance times the unit vector. Now the masses, the quantity that appear here are called gravitational masses. Okay, I mean, in principle, it is some parameter. A priori, there is no reason to believe or assume that the masses that appear here are the same as the masses that appear in Newton's second law. Okay, so we will allow them to be different. Okay, so the gravitational mass is the mass that appears in Newton's law of gravity. Okay. Yeah. So I'm going to discuss this in more detail when we talk about Kepler's laws and so on, but a brief comment about it now. It's quite interesting. So let us now consider a specific situation. Let us focus on the gravitational force of the Earth on small bodies near its surface. Okay, so we've got the Earth and we've got a stone near its surface. Yeah. Now at the surface of the Earth, the force on a gravitational mass mg, so the stone has mass mg. Yeah. Let us suppose, well, that force is given by, according to Newton's law, minus g gravitational mass of the Earth, gravitational mass of the stone, of course, again r hat divided by r squared, where now r squared is the square of the radius of the Earth, okay, because we are very close to the surface. Yeah, so me is the gravitational mass of the Earth and re is the radius of the Earth. Okay, so from this formula, we define the so-called acceleration due to gravity. Okay, so there is this force that is acting on the body. So by Newton's second law, the body would accelerate and that acceleration vector is given by the force acting on it divided by the inertial mass. Okay, so suppose I put that in. So this is where something interesting happens. Putting that in, we get that the acceleration that the stone undergoes is given by GME times gravitational mass of the stone divided by inertial mass of the stone divided by radius squared. Okay, so this downward pointing acceleration is called the acceleration due to gravity and is denoted by a boldface G. Okay, so it's a vector, it's boldface G. Okay, this is called acceleration due to gravity.
So can you please again define gravitational mass?
Gravitational mass is the parameter appearing in Newton's law of gravity. Full stop. So, see, I am, for some reason, after doing some experiments, observing planetary motion and so on, Newton, Kepler, Copernicus, and all their friends came up with some law. The law said that planets have some attribute. There are many attributes. It has a color, it has some smell, yeah, it has some taste, and so on. Yeah, there's one more attribute that we call its gravitational mass, and they are suggesting that the force between a planet and sun is proportional to this attribute, which we call gravitational mass. If you don't like the name gravitational mass, you call it by some other name. Yeah, but it's our agreement that we will call it the gravitational mass. A priori, this has nothing to do with Newton's second law. Okay? Newton's second law is a completely different statement. It tells you how a body will accelerate if you apply a force. So these are different concepts. Similarly, forget about Newton and company. Suppose you go a few years later and think of Coulomb and company. They're looking at charges, and they discover by some complicated procedure of observing charges that two charges exert a force on each other. Now, that force between charges depends on some attribute of that charge, some property of that charge, some feature of that charge. You have to give some name to that feature of the charge. We call it the charge of the charge. Okay, we don't call it the mass. Okay, it is some attribute. We call it the charge. Same way here, whatever is controlling the strength with which the sun is pulling the earth, we call it the gravitational mass. Okay, it is just a name. All right. Okay. So are you with me here? I have found the acceleration due to gravity on a mass mi and found that it has this formula, okay, near the Earth's surface. Okay, I hope that is clear. Okay, now comes a remarkable and surprising experimental observation. This again goes back to Galileo's time. So the surprising experimental observation is that the acceleration due to gravity is the same for all bodies. Okay? So whether it was a stone, a big rock, or a pencil, turns out that they all exhibit the same acceleration. So you take a rock, a stone, a pencil, all at the same height, drop them, they all accelerate in the same manner, they all reach the ground at the same time. Okay. So this is a absolutely remarkable experimental observation. You may think that a big rock would fall faster, yeah, or turns out it's not true. Okay, so the story of different objects falling in unison, that is at the same rate, the same manner, from the Leaning Tower of Pisa is a way to remember this. Okay, so it's not clear that Galileo has performed this experiment. Others have done it, but it's not clear that Galileo did. But anyway, he does describe it. He does mention this principle or this observation. So there is no mention about leaning of Tower of Pisa as far as his work is concerned. So the magnitude of this acceleration is first, it points downwards, and it's same for all bodies, no matter how heavy they are, no matter how big they are, no matter what the shape is. It is independent of the shape of the body. It is independent of how many people are needed to carry the body. Yeah. So the magnitude of this acceleration is called small g without the boldface, and is approximately 9.8 meters per second squared. Okay, so these are the experimental observations. Now let us combine it with the Newton's law and say what we can say. What we have observed then is that this acceleration A, which has now been called g, is the same for all bodies. That is, it is independent of the body. Therefore, the ratio mg over mi, namely the ratio of gravitational to inertial masses of a stone, must be the same as the ratio of gravitation to inertial masses of this bottle. Okay, no matter how much water there is in the bottle. Okay, so it takes some digesting. Yeah, and it took many years to come to this observation. It is not such a difficult experiment to perform. So by observing this constant ratio, so this ratio is a constant for all bodies. So the idea is to observe this constant ratio. So that ratio has some value. Okay, according to our setup, it has some value. Yeah, according to our principles, it has some value. Whatever that value may be, we will absorb that value into G. So that is, we will redefine capital G to include that constant. And thereby, so if it was some value like 23.4, we will absorb that 23.4 into G and say that Mi and Mg are equal. Okay, because anyway, the ratio is some constant. I will take that constant to be 1 by absorbing it into G. Okay, so it is possible by redefining Newton's gravitational constant G to assign gravitational mass equal to inertial mass. Okay, this is called the principle of equivalence of inertial and gravitational masses. Okay, so we have used, of course, a very important and remarkable experimental observation from Galileo's time. Yeah. So since we,
I don't know if it's true or not, but didn't Einstein say that they are always not equal?
Okay, no, this goes back much before Einstein. Yeah, yeah. So this principle is really due to Galileo. Einstein has also used the equivalence principle at a much more deeper level, but it starts from this. Yeah, so we will restate the equivalence principle in another way also later on. Yeah, in terms of gravitational fields and yeah, acceleration and so on. And then Einstein uses that formulation and extends it further. So, but the essential idea is much older. Yeah. Yeah. So there are various versions of the equivalence principle and so on, but here I am specifically speaking about the equivalence between inertial and gravitational masses. So it is a very simple statement, and I hope I have conveyed it to you. It is the remarkable fact that the mass of a body that appears in Newton's second law of motion is the same number as appears in Newton's law of gravity. Okay, by suitable redefinition of Newton's gravitational constant, this can be arranged. Okay, that is the claim. Yeah. Okay, so since we have already assigned inertial masses to bodies, the equivalence principle gives a way of assigning gravitational masses as well. Okay, so now we have a way of assigning gravitational masses as well. And henceforth, we will not make a distinction between inertial and gravitational masses. Okay, I mean, generally speaking, when you do other problems and so on, or other general discussions, we will not make a distinction between the two. Except when we want to focus on this issue, then we will come back to it. Okay, so the key observation, yeah, even if you didn't follow my argument, the thing to remember really is that all bodies, irrespective of their constitution, size, shape, etc., accelerate in the same manner above the surface of the Earth. Okay, so this is an absolutely remarkable observation, which I would like you to take away. Okay, any question about this? Okay. Of course, if you go to different heights above the Earth, these accelerations can be different. Okay, so it's at a common height that we are speaking. And okay, there are other ways to violate this. Suppose you take a feather and a stone, they don't accelerate in the same manner, but that is for other reasons, because a feather feels the wind and the buoyant force and all much more strongly, so of air, so that has other effects. So you are supposed to remove those effects. You are supposed to account for that, or not choose bodies which are subject to such forces in such a large measure. Okay. Now I want to define another concept called the weight of a body. Okay, so the weight of a body is defined as the Earth's gravitational force acting on it. Okay, this is our definition. Okay, so that's how we're going to define it. Now, at the surface of the Earth, let's see what this is. At the surface of Earth, the weight of a body of mass m is given by W, so boldface W. It is simply the force of the Earth on the body. Okay, that is all we need to look at. And we have already developed the formula for that. Yeah, so it is minus capital G mass of Earth times mass of body divided by RE squared. Of course, points downwards. So we have already introduced this acceleration due to gravity vector, which is minus G ME by RE squared R hat. Okay, so we can write the weight of the body as mass times acceleration due to gravity. Okay. Okay, so anyway, I hope as part of this discussion, you have realized where this acceleration due to gravity comes from in the context of Newton's law of gravitation. Okay, so it is something that can be deduced from it. Now, this weight is a force. Okay, so that is how we have defined it. So it is a force. So it must be measured in newtons, in SI units. And let me also emphasize that the weight as defined above is independent of the motion of the body. Yeah. Doesn't matter whether this stone was being thrown, was held fixed, all that doesn't matter. Yeah, doesn't even matter whether it's accelerating downwards. At any instant, it is at some location. You can find the force that the Earth exerts on it. That is defined as its weight. Right. Okay. Now, briefly, I want to introduce another concept called normal reaction. But any question before I do that? Okay, there is a related concept. There's a concept related to the weight of a body that is sometimes confused with it. So let us be a bit clear about this. So consider a body of mass m at rest on the Earth. Okay, so body of mass m at rest on the Earth. Okay, now Newton's second law would tell us, because it's at rest, it's not moving vertically, there is no acceleration. Mass times acceleration is 0, but that must be equal to the force. So the net force on the body must be 0. In other words, the forces acting on this body must be balanced in the vertical direction. Okay, let's look at the vertical direction. So we already know that the earth is pulling this mass down with a force m times g, and therefore the floor must, I mean, if this was the only force, then it would be unbalanced and the particle would accelerate. So there must be some other force acting on it. We call this force the normal reaction force that the floor exerts on the body. Yeah, and Newton's second law would tell us that its magnitude has to be minus mg, pointing upwards. Okay. So this is the force that the floor exerts to support the body. Yeah, so it's the force that the floor exerts, or if not a floor, if I was balancing it on my palm, my palm and arm would have to exert a force upward on the body to support it. Okay, that is called N. And by Newton's second law, it is equal to minus mg. Okay, so, all right. Any question about this? Let me be clear that we are considering the body. And we are asking what are the forces acting on the body. So there are two such forces. One is the force due to gravity. The other is the upward force due to my hand on the body. Okay, so these are the two forces. I am not considering what the force on the earth is. I am not asking what the force on my hand is. All such are different questions. Okay, so in order to apply Newton's second law, focus on a point particle, focus on a body and ask what the forces acting on it are. It's easy to confuse yourself by looking at forces acting on different bodies and try to apply some law to it. That is not the point. Okay, let us change the situation a little bit and see. I mean, this is again just an application of Newton's second law. That is my purpose here. Yeah, because we just learned Newton's second law. Let us apply it to one more context. Now, suppose the body is in an elevator, a lift that accelerates upwards at the rate a. Okay, so our lift is moving upwards, not just moving upwards, it's accelerating upwards at the acceleration a. Now, and we have the mass again sitting in that elevator. Now the force due to gravity on the mass, yeah, remember that force doesn't depend on whether the mass is moving, accelerating, all that doesn't matter. The force is given by Newton's law of gravity, and so the force due to gravity on the mass is still its weight. That has not changed. It is mg pointing downwards. All right. Now let us apply Newton's second law. Of course, if the mass is on the floor of the elevator, then the floor of the elevator is exerting some force on the body. If you didn't believe me, put your hand below the body and you will notice that, or you stand in the elevator and try to support the body, you will have to apply some force. Okay, so that is the force we are talking about. So Newton's second law, viewed from an inertial frame, namely observer standing on the earth at rest and watching this elevator go up, watching the body inside the elevator go up, that person is going to say that the body is accelerating. And not only that, accelerating at the same rate as the elevator, just moving with the elevator. So mass times acceleration must be equal to the total force on that concrete block or body. There are two parts to this force. One is the normal force directed upwards and the weight of the body W. So this is what Newton's second law says. Newton's second law for the body in the elevator. Okay, so we can of course rearrange and write the normal reaction force as m times a minus g. Okay, now let's look at this a little carefully and interpret it. So okay, this my picture is already here. So we are looking at the forces acting on this body. So there is the normal reaction force upwards and the gravitational force downwards. Yeah, and Newton's second law, if I just, so N points upwards, A points upwards as well, and G points downwards. Okay, N and A both point upwards and G points downwards. Yeah, so A and G point in opposite directions. So when I look at A minus G, in magnitude, it is actually A plus G. Okay, so suppose we say that upwards is the positive direction, then minus G also points upwards, A points upwards. So A minus G is actually the sum of the magnitudes. So we conclude that the magnitude of this normal reaction force is mass times A plus G. Okay. Okay, now what is the meaning of this normal reaction force or interpretation? This is the force that the floor of the elevator must exert upwards to support the body. Right? That is how we introduced it. This is the force that my hand must impart on the body to support it, to keep it from falling down. Okay, the magnitude of this normal reaction force, we notice, exceeds the magnitude of the weight of the body. It's more than the weight of the body in this context. Yeah. So it would be wrong to say that the normal reaction is always equal to the weight of the body. Yeah, that is not the case. We have to work out in each situation and find out. Yeah, and furthermore, a weighing scale is usually calibrated to read the value of N upon G, magnitude of N upon G. Okay, so that's how the numbers in a weighing scale are set up to read this number. So in particular, it will mean that a weighing scale, a weighing machine, if you are standing on a weighing machine in a lift that is going upwards, accelerating upwards, then it is going to read a value which is more than your mass. By your mass, I mean the value it reads when you are not in an accelerating elevator. And this is something we are familiar with. When we go up in an elevator, we feel that the floor is exerting a force on us, which is more than what we would feel when the elevator is at rest or uniformly moving also. Okay, so that is one more example of Newton's second law. All right, I want to give one more example of a force. I just have enough time for that, hopefully. Yeah. Okay, so this is called the electrostatic force. Now, charged particles, that is bodies of a certain sort, exert electrostatic forces on each other. Okay, so I mean, this has a long history. I don't intend to discuss that here right now, but it turns out that certain objects can be made to be charged, like rubbing them on some wool and such things. Yeah. Essentially, doing that kind of process pulls off some electrons from the surface, and the body becomes charged, and it manifests this charge by exerting forces on other charged objects. So charged objects are found to attract or repel. And the force between point charges is summarized in Coulomb's law. Yeah, from which country was Coulomb, by the way?
So was he from France?
Indeed, you're right. Yeah, so you're quite right. Okay. Yeah, so and Coulomb's law is very similar to Newton's law of gravitation between point masses. So if you replace the masses by the charges and Newton's gravitational constant with another constant, then essentially you get Coulomb's law. There's one small difference. So let me mention that. So first of all, the Coulomb's law of force between two charges is proportional to the product of the electric charges and falls off inversely with the square of the distance. Okay. So to that extent, it's very similar to Newton's law. Only one thing is that the charge need not be a positive quantity. Masses are positive. The charge need not be positive. It can have either sign. And that is to incorporate the fact, the observed fact, that charged particles can repel or attract. Okay, so So while masses always attract, like charges, namely those of the same sign, repel, and unlike charges attract. Okay. So, okay, so much for the electrostatic force. You will learn a lot more about this in a course on electricity and magnetism. Yeah. But I want to give other examples of forces. Many forces we are familiar with have their microscopic origin in electrostatic forces between molecules. Okay. In fact, somebody had asked this even earlier about friction. So the frictional force between a body and a surface, yeah, that is something we are familiar with. If we try to move a body on a surface, we find that there is an opposing frictional force. There's another force called viscous force, the viscous force between layers of a fluid. If you have layers of fluid in motion, so a layer of fluid in motion, either above a surface, so you have a surface and fluid moving over it, then one finds that the fluid velocity, when you approach the surface, becomes smaller and smaller. And at the surface, the fluid basically sticks to the surface. And there is no velocity at all. Okay, so this is attributed to viscosity with the surface.
So can we say all contact forces in the macroscopic world are generally formed due to electrostatic forces?
Correct. Yeah, that's by and large correct. Yeah. Yeah. Indeed. Yeah. So, by the way, I misspoke slightly here. I mean, this is a frictional force between the fluid and the surface. Viscosity is a word used more for the frictional force between layers of a fluid, not between fluid and the surface. Yeah. So if you have two layers of fluid in relative motion, one fast layer and one slow layer, or one layer moving this way and one layer moving that way, then there is a frictional force between them. Yeah. And yes, this is an example of a contact kind of force between two layers of fluid or between two bodies. And they have electrostatic electrical origin. Yeah. So they are macroscopic manifestations of electric forces. In fact, even the force that a stretched string or a rubber band exerts has its microscopic origin in electric forces between the molecules. Okay, so all of these come from that. So electric forces they have manifestations that we are very, very familiar with, even though the objects we deal with may not be charged. So that's the remarkable thing. Macroscopic objects are not charged. Okay, I mean, they have zero net charge, but nevertheless, there is a residual effect of the forces between elementary charges, atoms, molecules, electrons, that survives even at macroscopic lengths. And that we can very easily see. Yeah, of course, to deduce their origin through microscopic considerations is quite challenging, but anyway. So for this reason, we say that the electric force is a fundamental force, while friction and viscosity are called emergent or phenomenological forces. So that is a distinction that we sometimes make. Electric forces are sort of the basic force, fundamental force between microscopic objects, and their macroscopic manifestation is called an emergent force, yeah, or sometimes called a phenomenological force. Okay, this is a fancy term. Yeah.
Emergent, what do you mean by emergent force?
Yeah, emergent is a word used to describe phenomena that emerge when many particles or constituents interact. Okay, so Coulomb tells you we have 2 point charges, how they behave. Okay, or 3. Yeah, but suppose you have a million of them or 10 to the 24 of them, then the resulting forces may look very different if you don't want to pay attention to individual molecules, but you want to look at a whole block of wood or something. Yeah. Then the emergent force between that block of wood and the floor has its microscopic origin in Coulomb's law and Biot-Savart law and so on, but looks nothing like an electric force. So that is why they are called emergent. Okay, so as Kaustubh, I think, mentioned, friction and viscosity are also examples of contact forces. They are forces exerted when bodies are in contact. Okay. Now, though these forces arise from electrostatic interactions, by these I mean things like viscosity and friction, yeah, it is often not practical to deduce their strength from microscopic considerations. Okay, it's practically hopeless to try to figure out the frictional force between a car tire and the road by appealing to Coulomb's law and some force between charges. Okay. It's very, very difficult to do that. Instead, we look at these macroscopic phenomena, observe them, and deduce some general features. They are usually described via effective macroscopic formulae based on experimental measurements. An example of that is Hooke's law for a spring. Okay, I mean, as I said, the force in a spring is due to interactions between molecules, but it is hopeless trying to figure that out. Instead, we observe a bunch of springs and see how it presses against objects, how much force, and so on, and then come to some conclusion about the nature of that force. Maybe that force is proportional to the extension of the spring from equilibrium, yeah, or maybe quadratically in the extension, that kind of thing. We build some picture of the force that way. Yeah. So a couple of examples of that. Oh, I realize I have now run out of time. So perhaps these examples have to be discussed next time. So any question before we stop here?
Sir, in this class, by any chance, have you discussed what a force is, definition of force?
No, I have said that a force is something that we are introducing operationally. It is that which allows me to hit my head. Yeah, it is that kind of thing. It doesn't have an origin through geometric constructions. However, forces in more sophisticated treatments of physics, we have other principles at our disposal, various symmetry principles and beliefs and so on, and we are able to define forces through those procedures. So this is a long story. At present, force is doesn't have some mathematical definition like acceleration does. And we also gave an operational way of deducing the gravitational force present in this room by observing infinitesimal accelerations of particles. So that is another thing we did. So we are building up a picture here.
And yeah. Sir, a second question would be, from how far, from how tall, like height, from what height should I throw two objects and see them fall at the same time, in order to confirm my belief that there is a uniform acceleration?
Yeah, the height doesn't matter. It is really a question of what accuracy you wish to achieve and how accurate your time measuring devices and so on are.
Yeah. My question really is like, is the Leaning Tower of Pisa tall enough to perceive that?
Yeah, it's possible. It is tall enough. Yeah, this has been actually done from not just Leaning Tower, for other towers. It has been done not just now. It has been done even a couple of 100 years ago, and it has been verified even with the clocks available at that time. So, yeah, that height is adequate to. Of course, you can get it to a certain accuracy. If you want to improve the accuracy, you have to go either to a greater height or to get a better clock. Yeah. So, but to the accuracy available to people at that time, it is adequate to confirm this assertion.
Okay, sir. Thank you very much.
Whereas a much smaller height, it will be difficult to check it. Yeah, you are right. I mean, just within this room, it would be somewhat harder. Yeah. Okay, any other question? Okay, if not, let us meet again on Tuesday. Have a good afternoon. Thank you.